Hello everyone, and welcome back to the channel. Every year, the world turns its attention to Stockholm as the Nobel Prizes are announced, honoring breakthroughs that have fundamentally reshaped our understanding of the world. And for a physicist, for a cosmic enthusiast, the prize in physics holds a special place. It's a celebration of human curiosity pushed to its absolute limits. Today, we're going on a journey through the 21st century to count down what I consider the 5 most significant physics Nobel Prizes awarded since the year 2000. It's a celebration of the ideas that have rocked the foundations of cosmology and particle physics. Now I have to be clear, this list is completely subjective. It's my personal take. I've chosen these 5 based on a few criteria: their sheer cosmic impact, the elegance and, dare I say, simplicity of the core idea, and how much they've captured the public's imagination, reaching beyond the lab and into our collective consciousness. These are the discoveries that make you lean back, look up at the night sky, and just say, wow. They're the ideas that have opened up entirely new windows onto the universe, revealing mysteries we didn't even know existed. So get ready. We're about to explore ghostly particles that change their identity, a new state of matter colder than deep space, the particle that gives the universe its substance. The shocking revelation that our cosmos is being pushed apart by a mysterious force, and a discovery that lets us listen to the symphony of space-time itself. We're counting down from number 5 to number 1. Let's get started. This is the Cosmic Honor Roll, the best of the best. Kicking off our list at number 5 is the 2015 Nobel Prize, awarded to Takaaki Kajita and Arthur B. MacDonald. And what did they discover? They solved a cosmic mystery involving one of the universe's most elusive, most ghostly particles, the neutrino. For decades we had a serious problem. Our theories, which are really good, predicted a certain number of neutrinos should be streaming from the sun and reaching our detectors here on Earth. But when we looked, we were coming up short. We were only finding about a third of what we expected. It was called the solar neutrino problem, and it was a huge headache. Where were the missing neutrinos going? Kajita and MacDonald, through 2 completely independent and brilliant experiments, Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada, found the answer. The neutrinos weren't missing at all. They were changing. You see, neutrinos come in 3 flavors: electron, muon, and tau. What these experiments proved is that neutrinos can spontaneously change or oscillate from one flavor to another as they travel through space. It's like you threw a baseball, and by the time it reached the catcher's mitt, it had turned into a basketball. This was a mind-bending revelation on its own, but the implications were even more profound. According to the standard model of particle physics, our best, most tested rulebook for the subatomic world, particles can only oscillate if they have mass. And for the longest time, the standard model insisted that neutrinos were massless. Well, Kajita and MacDonald's work proved the standard model wrong, or at least incomplete. By showing that neutrinos oscillate, they proved that neutrinos must have mass, however tiny. This discovery didn't just solve a long-standing puzzle, it cracked open the door to physics beyond the standard model, hinting at a deeper, richer reality we have yet to fully understand. Coming in at number 4 is a discovery that sounds like it's straight out of science fiction. The 2001 Nobel Prize was awarded to Eric Cornell, Wolfgang Ketteler, and Carl Wieman for creating a completely new state of matter, the Bose-Einstein condensate. We all learn about solids, liquids, and gases in school. Some of us even get to plasma, the 4th state, but this is the 5th state of matter, and to create it, you need to get things cold. Not just winter in Antarctica cold, but colder than anything in the natural universe. We're talking billionths of a degree above absolute zero. So what happens when you get a cloud of atoms that cold? Their quantum nature takes over. In our warm, everyday world, atoms act like individual billiard balls, bouncing around independently. But as you cool them down to these extreme temperatures, they slow down, way down. Their quantum waves, which describe their probable location, start to spread out and overlap. And then, at that critical temperature, something magical happens. The individual identities of thousands, even millions of atoms dissolve. They merge into a single, giant superatom, all behaving in perfect unison, described by a single quantum wave. This isn't just a party trick for physicists. Bose-Einstein condensates, or BECs, are a macroscopic window into the bizarre world of quantum mechanics. They allow us to directly observe quantum phenomena that are usually hidden at the subatomic level. It's like being able to see the strange rules of the quantum world played out on a scale large enough for us to study directly. This breakthrough has paved the way for advancements in atom lasers, quantum computing, and ultra-precise measurements. It's a testament to the fact that nearly a century after Einstein and Bose first theorized it, we could finally enter the lab and build their quantum dream. Our number 3 spot goes to a discovery that was decades in the making, really the culmination of one of the greatest scientific quests in human history. The 2013 Nobel Prize went to François Englert and Peter Higgs for their theoretical prediction of a mechanism that gives fundamental particles their mass. And by extension, the prize celebrated the 2012 discovery of the particle associated with that mechanism, the Higgs boson. For half a century, the Higgs boson was the missing puzzle piece of the standard model of particle physics. We knew particles like electrons and quarks had mass, but we had no idea why. What gives something substance? The theory, proposed back in the 1960s, was elegant. It postulated that the entire universe is filled with an invisible energy field, now known as the Higgs field. Think of it like cosmic molasses pervading all of space. As particles move through this field, they interact with it. Some particles, like photons, zip right through without any interaction, and so they remain massless. But other particles get stuck, they drag against the field, and this resistance to motion, this interaction, is what we perceive as mass. The more a particle interacts with the field, the more massive it is. But a theory is just a theory until you can prove it. And to prove the existence of the Higgs field, you had to excite it. You had to hit it hard enough to knock a particle loose from it, the Higgs boson. That's where the Large Hadron Collider at CERN comes in. It's a 27-kilometer ring designed to smash protons together at nearly the speed of light, recreating the energy conditions of the early universe. After sifting through the debris of trillions upon trillions of collisions, scientists found it the telltale signature of the Higgs boson. It was a monumental achievement, confirming the mechanism that gives our universe, and us, substance. We're almost at the top. My pick for the second most significant prize of the century is one that completely blindsided the scientific community and rewrote our cosmic destiny. The 2011 Nobel Prize was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for a discovery that was as shocking as it was profound. The expansion of the universe is accelerating. For most of the 20th century, we had a cosmic debate going. We knew the universe was expanding since Hubble's discovery in the 1920s. The big question was, what happens next? Would gravity eventually win, pulling everything back together in a big crunch? Or would it expand forever, but slow down over time? These teams set out to answer that question by looking at distant type Ia supernovae. These exploding stars are incredibly useful. They act as standard candles. Because they all have roughly the same intrinsic brightness, we can look at how faint they appear to us to determine how far away they are. And by measuring their redshift, we can tell how fast they're moving away from us. The plan was to measure the cosmic deceleration. They were trying to find out by how much the expansion was slowing down. But that's not what they found, not even close. When the data came in, it was stunning. The most distant supernovae were even fainter than they should have been, which meant they were even farther away than predicted. The only way to explain this was if the expansion of the universe hadn't been slowing down at all. In fact, for the last 5 billion years or so, it's been speeding up. Something is pushing the universe apart, counteracting gravity on the largest scales. We call this mysterious, repulsive force dark energy. It makes up nearly 70% of the universe, and we have almost no idea what it is. This discovery didn't just answer a question, it threw open the door to the single biggest mystery in all of physics. And here we are, at number 1. For me, the most significant, the most poetic, the most paradigm-shifting physics Nobel Prize of the 21st century so far is the 2017 prize, awarded to Rainer Weiss, Barry Barish, and Kip Thorne. This prize celebrates an achievement a century in the making, the first direct detection of gravitational waves. Back in 1916, Albert Einstein, with his general theory of relativity, told us that space and time are not a static stage. They are a dynamic fabric, a four-dimensional continuum called space-time. And when massive objects like black holes or neutron stars accelerate, they create ripples in this fabric, like a boat moving through water. These are gravitational waves. For 100 years, these waves were purely theoretical. They were so unbelievably faint that even Einstein himself doubted we could ever build an instrument sensitive enough to detect them. The challenge is immense. By the time a gravitational wave from a distant cosmic cataclysm reaches Earth, the ripple it creates is astoundingly small. We're talking about a distortion in space smaller than the width of a proton, over a distance of several kilometers. Detecting that is one of the greatest technological feats humanity has ever accomplished. And it was accomplished by the Laser Interferometer Gravitational Wave Observatory, or LIGO. On September 14, 2015, LIGO's twin detectors, separated by thousands of kilometers, both registered a chirp. It was the unmistakable sound of two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging 1 billion light-years away. For the first time, we didn't just the universe, we it. This wasn't just a confirmation of Einstein's theory. It was the birth of an entirely new field gravitational wave astronomy. It has given us a completely new sense with which to explore the cosmos, allowing us to witness the most violent and energetic events in the universe that are completely dark to our telescopes. It's a new era of discovery, and we're just getting started. And there you have it, my top 5 physics Nobel Prizes of the 21st century. From the quantum weirdness of neutrinos and condensates to the cosmic mysteries of dark energy and the symphony of space-time itself. Each of these discoveries represents a monumental leap in our quest to understand the universe. They are a testament to human ingenuity, to our relentless drive to ask why and how, and to build incredible machines to find the answers. These are the shoulders of giants upon which the next generation of physicists will stand. But as I said at the beginning, this is just my list. The beauty of science is that what one person finds profound, another might see as a stepping stone to something else. The history of science is rich and interconnected, and you could easily make a case for other groundbreaking Nobel Prizes from this century. The discovery of graphene, for example, or the development of blue LEDs, which have transformed our world. The choices are as vast and varied as the cosmos itself, and every one of them has a story worth telling. So now, I want to turn it over to you, my fellow cosmic explorers. What do you think? Did I get it right? Did I miss your favorite Nobel-winning discovery? Head down to the comments and let me know. What would your top 5 list look like? Let's get a conversation started about the science that inspires you the most. Argue for your picks. I want to hear what resonates with you. Until next time, keep looking up.